Okay, as I mentioned in the last week, I will do these presentations in English to improve our English communication skills. But unfortunately, I'm still not perfect in English, so please excuse about some unnatural or ungrammatical expressions. And if you have questions, please ask me whenever you have in either in English or Korean. I will answer in each language. Okay. The topic I want to discuss today is the Hubble tension, which is the one of the hardest topic in current cosmology. And I refer most content of these presentations from their papers. I don't know how to pronounce, and some contents came from Wikipedia. The documents about biometric gravity and baryon acoustic oscillation. So today I will briefly review some cosmology knowledge and then explain what the expansion of universe means in the perspective of general relativity, and show how to measure the Hubble constant and the Hubble tensions related to that measurement, and introduce some solutions for that tension. Okay, first, let's review some cosmological knowledge. As you all know, the universe is expanding and has been expanding by the Hubble law, V equals H naught D. And the universe is composed of three kinds of components. First is matter, which means particles with high mass and low velocity, and the radiations, which means particles with low mass, so that it has a very high velocity, like a photon, and the darker energy, some unknown energy, which is known to accelerate expansion. And these three components follows the equation of state, which is the equation that connected the pressures and density of that components. So for the case of matter, the pressure is always zero, and the pressure of the radiation is the 1/3 times its density. And you should know that the concept of cosmic microwave background, CMB, 3 million years after the Big Bang, the temperature had dropped enough for nuclear to catch electrons, so they form the neutron atoms. But after the decoupling, the photon finally became free from their interactions. So the other photons is observed now as a form of microwave, which has a temperature of 2.7 Kelvin. This is the picture of the CMB. You can see that there is a little uniformness, and this uniformness is order of 0.0057 Kelvin. So it is very, very homogeneous and isotropic. For YouTube watchers who don't know about these concepts, I will attach some links, maybe pop on here, so you can follow this. And with this knowledge, I will explain the meaning of the expansion of the universe. In 3D space, the distance between 2 points can be calculated by the sum of the scale of the difference of coordinate components, like this. And in a matrix form, it can be expressed like this by multiplication of matrix. And in special relativity, Einstein added a time term in this experiment with a coefficient minus c square, not -1, minus c square. And in here, S is an invariant because it is invariant in the for the change of coordinate system. And you can think of it as a distance in a space-time. And this matrix is called a metric tensor. Of course, tensor and matrix is a total different concept, but you can there would be no problem to think of it just as a matrix in this presentation. And in general relativity, metric tensor is not fixed to this form. It is variable. And the metric tensor indicates the curvature of the space-time. To understand this, you can imagine a right-angled triangle on the spherical shell. On the flat face, the sum of inner angle of the triangle is 118 degree, and the Pythagorean theorem does hold. But for a triangle on the spherical surface, the Pythagorean theorem does not hold. So the equations that express the distance should be changed on the curved space, and that is included in the metric tensors. For the case of universe, because the universe is homogeneous in large scale, so each metric should be independent on the space coordinates and the isotropy, which means we should see the same pictures, which direction I see. So it should be dependent on the direction. So the all metric components should have the same form. So the metric of the universe should have the form of like this. The time term is still minus c square, and the space term has a square, which is dependent only on time. Therefore, in the universe, physical distance between 2 points equals a times the difference of the components. And the expansion of the universe means that this a is increasing over time, so that even there is no movement for that object, the distance between 2 points is increasing over time. And the Hubble constant h is defined as a dot, the time derivative of a divided by a, and a current value of h is noted as h naught. And by the way, it is a convention to call these h naught at h0. So measuring this h naught is very important in cosmology because it shows the evolution of the universe. And h naught is usually expressed with the dimensionless parameter h by these equations. So the h is the measure of the h naught. The first method, which is very direct and simple, is using just Hubble law, measure distance and velocity, then we can get h naught by the Hubble law. Of course, it's not an exact method because h is changing over time. So the exact method should be more complex, but the overall structure is same: measuring distance and measuring velocity. Resistance velocity can be easily calculated by measuring the redshift. It is simple. The problem is to measure the distance. And in cosmological scale, the type 1 supernova is usually used to measure the distance. The second method is a little indirect and a little complicated one. It is using the inhomogeneity of the universe. As you saw in the CMB pictures, there is a little inhomogeneity in the universe. For the decoupling, so when the nuclear and electrons are bound by each electromagnetic interaction, gravity of the matter pulls the matter itself, and radiation pressures exert on the matter to push it to the outside directions. So these two forces create the wave. You can think of it the same mechanism as the sound wave in the air. But after the decoupling, the photon pressure is disappeared. Photon pressure disappeared, so this wave was fixed and remains invariant from that time. And we call the wavelengths of this wave as a sound horizon, RS. And this sound horizon can be detected on the CMB picture or the large scale survey of galaxy distribution. And because sound horizon analysis can be calculated theoretically, it can solve as a standard rulers, like the Taiwanese supernova solves as a standard candle. Sound speed, the speed of that wave for the decoupling is given by this form. And here, omega b is and omega gamma are measure of the density of baryon and radiation. And using that sound speed, we can calculate the value of the sound horizon through this formula. With this estimated value, we can compare the angular size of a certain structure and measure the distance, measure the angular distance to the structures. Then we can get H0 because the sound horizons depends on H value. And astronomers found that the values of H0 obtained from those two methods is different. At first, it seems just a problem of error. So they thought that it can these tensions will disappear if we can get a more exact measurement. But even after they got exact measurement, the tension is still obvious. So this tension is called Hubble tension, and it is becoming it is a rising topic in current cosmology. So there is a problem, then we should solve this. And it could be just due to observational or methodological problems. For example, some astronomers claimed that we live in the underdense region in this universe, so that the local measurement of the H0 is larger than the universe average, because the other overdense region will attract our underdense region, so the H0 around us is larger than the universe average. Unfortunately, this claim was refuted because it is found that the underdensity of our location is not enough low to explain the Hubble tension, but explanation like this might be solved, might solve the Hubble tension. This tension also reminds us a piece of science history. In late 18th century, most physicists thought that physics will be finished. The power of Newtonian physics and electromagnetic physics solves almost all problems in the world, and only two problems left at the time. The problem of ether, one matter propagates the lights, and the problem of the black body. But all you know is that two problems led to birth of modern physics. So these tensions also might be a door to the new physics. And among three components of the universe I mentioned, matter and radiations is measured with relatively high confidence by independent methods. So we can think that they are correctly measured. So the key component would be the dark energy. because because its character is still unknown. There might be two options to solve the Hubble tensions using dark energy. Firstly, assuming the both measurement is right, so the two method is right, we can check if there is a mechanism that accelerates the universe, expansion of the universe after the decoupling. It's called late dark energy. In general relativity, by the conservation of energy, the components should follow these equations. And you can notice that if the omega is lower than -1, time derivative of density is larger than 1. So the density of that component will continuously grow. So if the omega of the dark energy is lower than -1, it might explain the Hubble tensions. So these kinds of dark energy is called phantom dark energy. It's a little strange words because phantom means we don't know and dark means we don't know. So it is the unknown energy. But the field created by this dark energy is known to have negative kinetic energy and is very susceptible to vacuum instability. So it is not largely accepted by most physicists or astronomers. The second late dark energy is biometric gravity. As you can know in this name, its name, it is the gravity theory that assumes two metric tensor. One is just normal metric tensor I explained, and this theory claimed that there is another hidden metric tensor. In this theory, the Lagrangian have the form of like this. You don't have to know the details about these equations. You just know that there is two metric tensor, G and F, and a combining term. And here, E are elementary symmetric polynomials. You can think of it just the polynomial vector. And beta are bounding constants between two metric tensor. Among these beta values, let's assume that it just holds up to linear order. So the beta 1, not B, I did a mistake. Beta 0 and beta 1 is not a non-zero value. And it's known that for beta 1 lower than 0, can solve the Hubble tensions, but the data pushes beta 1 approach to 0, as you can see in this picture. To have a more confident value, the beta 1 should approach to 0. So it breaks the linear assumption, so it does not hold. And quadratic model assumes that it has beta 2 is also a non-zero value, setting beta 0 equals 0. And it also could solve the Hubble tensions, but the data pushes beta 2 to approach infinity value. So the quadratic term assumption is broken, so it cannot hold. And the third late dark energy is phenomenological dark energy. It is a theory that claims that at a certain moment, the density of the dark energy is phenomenologically changed. It can be divided into two models. The first is disappearing dark energy, which assumes that dark energy disappeared at a certain moment. And the second one is negative dark energy, which assumes at a certain moment the dark energy changed from negative values to the positive values, but both cannot relieve the tension. So the light dark energy seems to not to be able to solve the Hubble tension. The second theory is early dark energy. In this theory, we check the possibility of the estimated value of sound horizon is incorrect. Especially lower sound horizon indicates lower angular distance to the decoupling, because to have same angular size on the sky with the lower sound horizons, the distance to the decoupling should be lower, and this means the expansion rate is higher than we expected. One of this theory is dark radiations. It assumes there is an unknown relativistic energy component. So relativistic means it functions like radiations, which has an equation of state of 1/3, but it does not interact through electromagnetic forces. And comparing with the current data, astronomers found that it should have a density of order of radiation, and it can return the H value of 0.73, which is the same with the local measurement, the direct measurement of the H naught. And they also check the possibility of the other energy components which has a different equation of state, and they check the possibility and found that that dark energy component should have a equation of state which is lower than 1/3, but bigger than 0, as you can see in these pictures here. And it returns the value of 0.714, which also is also similar to the local measurement. So in summary, Hubble tension is the tension between the measurement from two methods, the direct methods and indirect methods. Although this tension may come from the observational or methodological problems, but still there is possibility of new physics for the dark energy. And until now, all dark energy seems to be more probable than light dark energy, but it's just theory. It's still not proven. Even we still don't know what exactly the dark energy is. So the more exact and model independent measurement is required, and the improvement and interactions with the physics is required to solve this problem. Thank you. And if you have a questions, please ask me.
사운드 호라이즌 설명하실 때 뭐가 인베리언트하다고 했는데 그걸 좀 다시 설명해 주실 수 있나요?
네, 여기서 보면은 원래 이 사운드 호라이즌이 생긴 이유가 레디에이션 프레셔랑 메러의 그래비티 때문이잖아요. 근데 근데 디커플링 이후에는 그 레디에이션 프레셔가 사라지니까 원래는 이 웨이브가 계속 변하고 있었단 말이죠. 우주가 팽창에 따라. 근데 레디에이션 프레셔가 사라지니까 그 상태로 웨이브가 고정이 되고, 그렇기 때문에 이 사운드 호라이즌이 스탠다드 룰러로서 기능할 수 있는 거죠. 만약에 이게 디커플링 이후에도 계속 변했다면은 얘는 스탠다드 룰러가 될 수 없겠죠.
근데 그래비티가 남아 있으면 계속 걔가 변화를 일으킬 수 있는 거 아닌가요?
그쵸, 변화가 일어나는데 그거는 이제 중력의 상호작용에 의한 예를 들어 뭐 은하를 형성한다든지 그런 변화지 전체적인 이런 러지 스케일에서의 물질 분포의 변화를 일으키지 않는다는 거죠. 그러니까 예를 들어서 이렇게 퍼져 있던 이 정도 크기로 퍼져 있던 물질들이 중력 수축을 해서 은하를 형성해서 이 정도 스케일로 줄어들었다 할지라도 그 은하들의 분포를 따져보면은 특정 웨이브의 분포를 따르고 있겠죠.
큰 스케일에서 봤을 때 인베리언트하다 뭐 이런 설명이죠.
그죠, 그죠. 코스몰로지는 언제나 럴리 스케일.
그 그거에 대한 단질문인데 그 사운드 호라이즌 잴 때는 디스턴스 레더에 의존을 안 하는 건가요?
디스턴스 레더는 우주론에서 이제 거리를 정의하는 방법이 여러 가지가 있잖아요. 그죠? 그럼 디스턴스 레더는 루미너스 디스턴스를 측정하는 방법이고 이거를 알기 위해서는 결국 앵귤러 사이즈를 비교하는 거라서 앵귤러 디스턴스를 비교해야 되는데 앵귤러 디스턴스는 우리가 그 구성 물질의 비율을 알고 있다면은 이론적으로 계산을 할 수가 있죠. 디커플링까지는. 왜냐하면 이 기준이 디커플링이니까 특정 레드시프트가 얼마인지 모르는 물체를 관측하는 게 아니라 디커플링까지의 앵귤러 디스턴스를 측정하는 거니까 이론적으로 예측할 수 있고 그래서 얘가 상당히 모델에 디펜던트합니다. 두 번째 방법은. 어떤 우주론 모델을 채택하느냐에 따라 값이 달라질 수도 있고 반면에 이제 로컬 메이저먼트는 되게 단순하고 상당히 모델 인디펜던트하죠.
혹시 발표자분께서는 어느 쪽이 조금 더 맞다고 생각하시는 그런 게 있나요?
제 생각은 아마 값은 로컬 메이저먼트 쪽이 가까운 것 같고 왜냐면은 지금 로컬이긴 한데 꽤 많이 레드시프트를 늘려봤거든요. 여러 가지 방법을 통해서 지금은 타이원 A를 얘기했지만 AGN을 이용해서 거리를 구한 논문도 있더라고요. 그것도 로컬 메이저먼트랑 일치하고 그 다음에 두 번째 방법이 너무 모델이 디펜던트해서 얘는 조금만 물리 과정 피직스가 조금만 달라져도 달라질 가능성이 내포하고 있어서 값 자체는 로컬이 맞지 않을까 생각하고 있습니다.
뭘
네.
거실 수 있나요?
뭘 걸어야 되나요?
그런
우주론 대토론 그때
그때 걸었나요, 뭔가를?
그때 그 이정욱 교수님께서 뭘 거셨지? 일단
그때 막
제 차는 못 걸겠고 뭘 걸까요?
그때 썰을 말씀해 주셨는데 막 어떤 천문학자들끼리 싸우는데 막 어떤 천문학자가 자기 재산의 3분의 1을 걸겠다 뭐 그리고 다른 천문학자가 그 사람의 재산의 3분의 1가 뭐 내 강아지를 걸겠다 뭐 이러고
네,
뭘
재산이 있어야 걸지 않겠습니까?
그것도 맞는 말입니다.
틀리면 그
뭐지?
이유로 음주를 하지 않겠습니다. 그럼 더 이상 질문이 없다면 여기서 제 발표는 마무리하도록 하겠습니다.